Okay, so last time we talked about the subatomic particles and a little bit of their effects, and now we're going to take a greater look at how each of those things affect things. For instance, we said that different number of protons make different atoms. That can be seen on any periodic table because the atomic mass number, the atomic number is simply the number of protons. And we'll be looking at the periodic table a good bit more, so we're not going to focus on that one in this video. This one's going to look at ions, so when we change the number of electrons, and isotopes, when we change the number of neutrons. First up is ions, meaning we're changing the number of electrons. They are one of the easiest things to change in an atom because most of the atoms, we'll find out there are a few exceptions, wish to either gain an electron, like chlorine over here, or lose an electron, like sodium here. You get a cation when the electron is lost because they're negatively charged. If it loses one, it becomes positively charged. So the way I always learn this is, since it's positively charged, lost an electron, cation, that T makes it look like a little plus in there. That means it is a positive ion. We call it an anion when it gains an electron, so it becomes negatively charged, because to add one more electron would make it more negative than neutral. Okay? This is an easy way to see when you look at the reaction between sodium and chlorine, or table salt, as you call it. It has an ionic bond, and basically sodium gives up one electron that goes to chlorine, so sodium becomes a cation, chlorine becomes an anion, and opposites attract, so they're pulled towards one another. Okay? This is mostly just a list of different types of positive ions, or cations, and negative anions, and it does give you an idea, a little simpler picture that you can draw in your notes if you want of what it's supposed to look like. But I mostly put this up there because of this one. Notice that we talked about different energy shales, and it gives a good idea of why these atoms might want to do this. So for sodium, for instance, it only has one electron in that outermost shell. We call that the valence shell. We'll get into that a little bit later. And so when it gives that one away, its next shell is filled up with electrons, which is what they want to do. They always want to have an outer shell that is filled. Chlorine, as we looked in the last one, it actually is only missing one from a full shell. So when it gains one, it then has a full shell. And so it's kind of the reason why these ions are made more often in some elements than others. So next up is isotopes. Isotopes, again, are basically an atom that has a different number of neutrons. So a lot of times you have the element that's been bombarded by loose neutrons because any of the subatomic particles can exist outside of an atom. However, protons, when they're consisted of a single atom, it's just considered a cation of hydrogen. But anyway, so neutrons bombard it, since they're the same mass as protons, they can actually end up hitting that nucleus and sticking, and it would end up making a different type of the same element, an isotope. It makes it unstable, though, because neutrons contribute a lot to the stability of the overall atom. That's why most of the isotopes that we're going to talk about are at least slightly radioactive. And so notice there's a whole different way of kind of writing these things. Isotope mass goes up here, atomic number goes on the bottom, and then the symbol. It's not too difficult to understand, but still something we might practice. Speaking of practice, why don't we try this out? Let's use a very famous example, carbon. In fact, have you ever heard of carbon-14? Well, it's not called carbon-14 because that's its atomic number. Carbon's atomic number is actually 6. But carbon-14, carbon would normally have a mass of 12, but since it has 2 extra neutrons, it actually has a 14. So carbon-14 would look something like this. So again, this up here is its new mass with the extra neutrons, making it an isotope. and this down here is just its atomic number, the number of protons. You always kind of need both of these because you're always able to figure out the number of neutrons by subtracting the number of protons from the mass. So we can tell in this one that 14 minus 6 is going to leave us with 8 neutrons, and it makes it somewhat unstable. What a lot of people don't realize is carbon-14 is only one isotope of carbon. There is another form called carbon-13. It just has 7 neutrons instead of the 8 that make up carbon-14. Now, this with 6 neutrons, this is carbon-12, but you don't need to call it carbon-12 because this is actually the correct amount of electrons and mass for carbon to have in it. So it really shouldn't be under the isotopes of carbon. Carbon-12 is base carbon. It's carbon in its neutral form. But this is just a little example to show a little bit more. I think that's enough for this time. Thanks.